Now let's go to fluids mechanics. When we're dealing with fluids, we're dealing with liquids and gases. Liquids and gases. And to study liquids and gases, we use some quantities that are very important, like density. Density, rho, right, is defined as mass divided by volume. We use density in physics and chemistry because it's constant, right? What happens if density is not constant? Well, in that case, we can use density equals to the change in mass with respect to the volume, right? The derivative. So we define this quantity is very important, mass divided by volume, which is density, that is used in the study of fluid mechanics. Okay, also we have another quantity, and that is pressure. Pressure is defined, that's the symbol for pressure, is defined as force divided by the area. Well, this force is the perpendicular component to the area. For example, imagine the surface and we have a force acting on the surface. What should be the pressure? The pressure is just this component perpendicular to the, this is the force, for example, it's gonna be the perpendicular component, right, of the force acting on this area. And then pressure is gonna be is this component perpendicular to the area divided by the area itself. That is pressure. So let's go for the unit. The unit for density, as we know, is gonna be kilograms per cubic meters. What about the unit for pressure? The unit for pressure we can use in the metric system, the unit of pascals. The name is Pascal. Pascal, PA. That's one of the units for pressure. We have another units like atmospheric pressure, or we have PSI, which is pounds per square inch. But in the metric system we use pascals. In this case, 1 pascal is equals to 1 Newton divided by square meters, which is the unit for the area. Correct? Perfect. So do we have pressure is equals to force divided by the area. Great. Now, what happens if the pressure, this is the case when pressure is constant. What happens if pressure is not constant? Well, in that case, we find the change in force is equals to pressure times the change in the area. Correct. This is the formula that we use when pressure is not constant. Correct. Perfect. Now let's go to some statements that we have in the study of fluid mechanics. Let's pay attention in this case to fluids at rest. Fluid right at rest. For example, imagine that we have a container, right, and we have a fluid in this container. It's found that the forces done by the fluid on the walls of the container must be perpendicular, right? The force must be perpendicular. What happens if the force is not perpendicular? For example, like in this case, if the force is not perpendicular, we can break that force into components. One in this direction, one going up. This is the force. This component is stopped by the wall, but this component produces motion of the fluid. But the statement is the fluid must be at rest. If the fluid must be at rest, forces are perpendicular to the wall of the container, right? Forces, so the forces are perpendicular to, right, the walls of container. Correct, this one is statement. If there's no perpendicular means that it's a component going in other direction, it produces motion. But the statement is that the fluid must be at rest. Perfect. This is one. What about in the case when we're looking for, it's the same container right here, correct? Now we're looking for the pressure on this bottom. How can we find that pressure? Well, how do we define pressure? Pressure is equals to force divided by area. What is the force acting on this area? Imagine this is the depth, H. Okay, depth. Okay, H. Perfect. Well, the force is just the weight, right? mg, the weight of the whole fluid acting on the bottom right here. So this equals to mg divided by the area. Correct? But how do we define mass? Let's use density instead of mass in this formula. It's gonna be density volume times g divided by the area. But what is volume? Volume of this amount of water in this container is H times the area. So pressure is equals to density area times H, G divided by area. So in this case, what should be the pressure? The pressure equals to density Hg. Correct? And we call this the gauge pressure. This is called the gauge pressure. Okay, so we have the gauge pressure is defined as density GH. Correct? So in this case, we can see that the pressure depends only on what? Depends on the density, the pressure on the bottom, right? Depends only on the density of the fluid and on the depth. Correct? Perfect. Now, what happens when we are dealing with pressure in all directions? For example, one more time, imagine this is the container right here. Okay, that's the container. We were dealing with a point at this depth, where the pressure is the same, right, in all directions. What happens in this position? Well, even though the pressure increases, but it's the same, right, in all directions. Okay, at the same depth, right, the pressure is the same in all directions. Okay, that's that statement. Also, we have that the pressure, as we can see from here, the pressure depends on what? On the density, on height, the depth, right? What happens if we change the shape of the container? Like in this case, we have this container right here. We have these different shapes like these ones, correct? Like this. Well, it's found that the pressure doesn't depend on the shape, depends only on the density of the fluid and height. For example, imagine it's at the same height right here. Oops, at the same height. Imagine it's at the same height, this point. And this is the water right here, right? This is water. Okay, well, we have the same H. Doesn't depend on the shape. The pressure at this point, at this position, depends only on one density, on one on what density and H, height. Okay, perfect. Now let's go to this situation. Imagine again that we have a container. We have a container one more time. Now let's take an element right here of the same fluid. Let's say water. This is what happens. Well, this is the dimension H, right? We have a pressure 2 times the area and pressure 1 times the area, right? They are the same, right, for this element of fluid. And then what do we have? Also we have weight, right? Weight, mg. Because this is an element of the fluid, that element is at rest, right? It's at rest. Okay, perfect. And then let's find the net force in the y direction. And we have that the net force is equals to Look, if we use pressure times the area, according to this formula, is gonna be the force, right? The force, let's say F2, let's call it F2, correct? Which is equals to P2 times A. And in this case, what do we have? We have that the net force is equals to forces acting outward. It's gonna be P2 times the area minus P1 times the area minus mg equals to 0. Correct? Let's solve for P2. Correct? This is equals to P1A plus mg. Right? Now let's solve for P2, right? P2 is equals to P1 plus mass G over the area. Now instead of mass, one more time, let's use density from here. And this is equals to P1 plus, what is the mass? It's going to be density of volume G divided by the area. But what is the volume, one more time, of this element? It's going to be H times A, right, the area. So this is equals to P1 plus density H times area G divided by area. Or it is equals to P1 plus density GH. Correct? Which is the same as this pressure. So the pressure on the bottom, right, is equals to the pressure on the top plus the gauge pressure. Correct? So we can represent this quantity in this way. Pressure on the bottom is equals to pressure on the top plus the gauge pressure. So the gauge pressure is just the difference between these two pressures. Correct? Perfect. Also, when we're dealing with, we found before the gauge pressure, remember? Now if we add the atmosphere, remember we found the pressure down on the bottom because of this amount of water, right? And this is the depth H. Now what happens if we add the atmospheric pressure? In that case, we create the absolute pressure. So absolute pressure, P absolute, is equals to atmospheric pressure plus the gauge pressure, which is density GH. Right? So we create the atmospheric pressure equals to 1 atm plus density GH. Right? Perfect. Now let's try to derive the atmospheric pressure. How is found? How is calculated? Let's do it. This experiment was done a long time ago by Torricelli. Torricelli was Galileo's disciple. And he did this experiment. He took this tube, long tube, right, about 1 meter long, and more or less 5 millimeters in diameter. And he took, this is was filled with mercury, okay, mercury, and he put this into this container, also with mercury, correct? And he found that this tube keeps some, we put it upside down, of course, and he found, right, that this tube keeps some height of mercury, right, like in this picture. Right here was vacuum, right, vacuum, and at this distance from the level of the mercury to the surface of this container is equals to 76 centimeters. This condition happened because of the atmospheric pressure. We mentioned in the previous analysis, right? Remember, if we have this container one more time, at this height, at this depth, right, the pressure is the same in all directions. The same paper here, the pressure is the same in all directions. What happens at this level, right? The pressure is the same, right, in all directions. But this is the same depth as at this position inside of the tube, right? the pressure is the same in all directions. So the pressure or force that keeps this amount of mercury at this height is the atmospheric pressure. This force at this level, this force at this level is the same as the atmospheric pressure outside. Correct? Now let's try to calculate this pressure. What's the pressure right here? Let's do it. Let's use the formula for pressure. Pressure is equals to force divided by the area. And what is the force in this case? Well, it's gonna be again the weight of the mercury. Correct? What is the weight of the mercury? Gonna be mg, right? And divided by the area. But instead of the mass, we use the density, and this is equals to density volume, correct, G divided by the area. But one more time, what should be the volume? The volume is equals to AH times the area, and at the end, what do we have? We create this formula, right? Density GH. By the time of Galileo Galilei, right, the density of mercury was known, right? Density for mercury is equals to 13,600 kilograms per cubic meter. When we substitute this value right here, what do we have? This is equals to 13,600, right, kilograms per cubic meter times 9.80 times meters per second square times what? 0.76 meters. It's found that this is equals to 1.013 times 10 to the 5th pascals. And that's 1 atm. So 1 atm, or atmospheric pressure, right? 1 atm, we call it this atm, or okay, 1 atm is equals to 1.013 times 10 to the 5th pascals. Also, this is equals to 1 atm atmospheric pressure is equals to 14.7 pounds per square inch, or psi. This is also equals to 76, right, centimeters of mercury, or this is equals to 760 millimeters of mercury. So these are other units that we use, right, for atmosphere, psi and millimeters of mercury. Correct? Perfect. Now let's go to Pascal's principle or Pascal's law. Okay, perfect. Pascal's law. Sometimes it's called Pascal's principle. Pascal's law. And it says that the pressure, if we have a fluid in a container, if we change the pressure of this fluid, the pressure is transmitted to the fluid, right, and is constant. For example, imagine that we have this container right here, and this is a movable piston, right? The same thing happens right here, movable piston. And in this case, well, the pressure is the same in all directions, correct? In the walls too. Imagine that we press, correct? We have a mass right here, right? A mass, which brings a force, right? And we have a force right here. Let's take this as the input force, and of course, let's holding this object, which has a force or weight, right? F2. Of course, the area of this piston is input area, and the area for this one is output area, for example. So the pressure, if we press this fluid, the pressure is transmitted, right, to all the walls of the containers, right, in all directions. Well, perpendicular to, remember it's perpendicular to the walls, right? And is the same. So this pressure is transmitted from this side to the other side. So means what? This principle says that input pressure is equals to output pressure. Okay, and what should be the input pressure? That be input force over input area must be equals to output force over output area. Actually, this behaves as a simple machine. A simple machine is a machine that multiplies forces. For example, let's see what happens when we're looking for the output force. The output force is equals to output area divided by input area times by the input force. Let's do one example. Imagine that the input force is equals to 100 newtons, correct? And also the output area is equals to 100 times the input area, correct? So what do we have then? Imagine that we substitute these values right here, and this is just 100. It's gonna be 100. This is output area, okay, divided by this input area times 100 newtons. When we multiply this, what do we have? Well, this is equals to what? 10,000, right? Newtons. See, with 100 newtons, we can create a 10,000 newtons. So we are multiplying forces like a simple machine, right? But also look, imagine that we have this situation. In this case, we are moving this piston to this position. At the beginning was this position, correct? At the beginning, and now we are right here. The same thing happens right here, right? Right here, at the beginning was, this is some x, right? Let's call this delta x1. The same thing happens right here, correct? This is delta x2, correct? So the when we apply a force right here, the input force, what happens? Well, we're moving this distance. The same thing happens on the other side. We move some distance, right? But when we apply the condition of volume, volume must be constant. It's the same. The same volume changes right here. The same volume changes right there, correct? So what do we have then? We have the volume 1 is equals to volume 2. But what is volume? Volume is area 1 delta x1, right? And volume 2 is what? Area 2 change in x2, correct? In the other side. Perfect. And then what do we have? Well, we can play with heights. Imagine we're looking for this difference. Delta h2 should be equals to what? Okay, should be equals to A1, area 1, area 2 times delta x1, correct? For example, in this case, once we know how much we're moving right here, we can now write how much is moving, right? This mass outward. Also, energy must be conserved, right? What is energy? Energy is a force times this, in this case, work, right? So we have that this input force, this is input force, correct? Input force, right? Or F1, or this is output force, okay? Like that, so perfect. It's gonna be the input force times this delta x1 is equals to output force, correct? Delta x2. So energy is conserved. In this case, we're dealing with work, right? Remember, work and energy are related. Okay, perfect. Also, look, imagine that we have this situation right here. Look, imagine that we have, let me make another one. Let me draw another one, another figure similar to this one. Okay, imagine we have this situation. Okay, and one more time, this is the piston at the beginning was right here, right? We apply a force. This is the input force. Again, this is the input area, or we can call it F1 and A1, the same thing. At the beginning, right, the piston was right here, and later, right, the piston, of course, is right here. Imagine we have this mass, okay, right here. Right, we're doing this and goes in that way. What should be then the pressure? How we can work with this? So we see that from the beginning, we're using Pascal's principle. What is Pascal's principle? Okay, Pascal's principle says that input pressure is equals to output pressure, right? Perfect. But in this case, look, we have applying a pressure right here because we have force divided by force divided by input area. But input area is equals to what? We have this force, right? This is the output force, and it'll be output force over output area. But also, look, we're moving upward this amount of fluid, right? This amount of fluid, this volume is also right above the original level. So we have to take into account the pressure, right, done by this amount of fluid. And this is equals to, we mentioned before, plus the gauge pressure, correct? We mentioned the pressure done by the amount of fluid on the surface. On the surface now is gonna be what? Density G, we can call it this, what? Delta X2, okay, delta X2. Correct, and we call this delta X1. So in general, we can see that the input pressure is equals to the output pressure plus density G, we call it delta X2 or H2, okay, H2, because we're dealing with H right here, okay, H right here, H2, or delta X, that is gonna be the same, right? Perfect. Now let's go to the next concept, which is Archimedes' principle. Okay, let's do it. Archimedes' principle. Remember, we're still working with fluids at rest. Great. Archimedes' principle. And it says that any object immersed in a fluid experiences an upward force. This upward force is called the buoyant force, and the buoyant force is equals to the fluid displaced by the object. So this is Archimedes' principle. Okay, it says that again, the buoyant force is equals to the weight of the fluid displaced by the object. And what is the weight? Is m, and that'll be m of the fluid displaced times g, or we can call this using density. It's gonna be density, the density of the fluid times volume of the fluid times g. And that's the buoyant force, right? Buoyant force, according to Archimedes' principle, is equals to the weight of the fluid displaced by this object. Why this force is present? Well, because of difference in pressure. For example, imagine that we have a container. Okay, we have a container with water, correct? And one more time, let's take this element, right? And as we did before, this is what? Pressure 1, area 1. What do we have right here? Pressure 2, area 2, correct? So how do we define the buoyant force then? The buoyant force is done because of the difference in pressure. The pressure on the bottom is larger than the pressure on the top, right? So we have an extra force. We have force going outward in this element of fluid. So what should be then that force? The force again, the net force is equals just to the buoyant force. And what is the buoyant force then? It's equals to the difference in these two forces. Remember, force in this case F2 is equals to P2A2 according to this equation. Correct? Perfect. So how do we have the net force equals to P2A2 minus what? P1A1. Correct, is the difference. And what is this? This is equals to what is p what p2 the area is the same, right? They're gonna be the same. Gonna be p2 minus p1, correct, times the area. The area is the same, right? Well, what is p2 minus p1? Well, we are going to this equation that we found before, right? p2 minus t1 is gonna be the gauge pressure. So this is equals to density GH times the area. But what is H times area? H times area, this is H one more time, it's just the volume. Okay, so this is equals to density G times volume. But density G times volume is just what? Is the weight of the fluid displaced, correct? And this equals to M of the fluid times G, right? Which is again the Archimedes principle, right? Perfect. Okay, now let's go to the last topic for this video, for this section. It's gonna be foreign object. Okay, let's do it. Let's do it. Foreign object. Okay, let me erase this principle. Objects. Okay, imagine that we have this block, right? Imagine this is the block right here. We have water in this way. Okay, let's bet this is what? This is, let's call this edge nut. We call this edge, right? The edge of the fluid, right? The height of the fluid, right? That is for this block, right? That is immersed in the fluid. Let's call it this HF. Correct. And now let's pay attention one more time in this figure, only in this part. One more time. This is HF, right? This is area on the bottom, right? This is area on the top. Perfect. Imagine it was like that. Great. Now let's see what happens. Force is acting. Well, we have the weight is acting, mg, that's the weight of the object, and what else? We have the buoyant force. This is floating, means it's in equilibrium. Let's find the net force. What should be the net force? The net force, remember, is the sum of the forces acting on the object, in this case in the y direction. It is equal to the buoyant force minus m, mass of the fluid, times g, and is equals to 0, right? Because it's at rest. Okay, great. What should be then the buoyant force? The buoyant force is equals to mass of the fluid times mass of the fluid, mass of the object, right? This is mass of the object, correct? Times g, which is the weight of the object in air, right? Perfect. But how do we define the buoyant force? Well, is equals to mass of the fluid times g. So then mass of the fluid displaced, right, which is this amount, correct? Times g equals to mass of the object times g. Correct, means what? Mass of the fluid is equals to mass of the object. Mass of the fluid displaced by this object, floating object. Perfect. Now let's go to densities. Because I want to take some dimensions from here. So mass is equals to density, in this case density of the fluid displaced times volume of the fluid displaced is equals to density of the object, right, times volume of the object. Okay, and what should be the volume displaced by the fluid? It's gonna be by the volume of the fluid displaced by the object. Okay, it's this one right here. So it's gonna be equals to what? It's equals to, one more time, density of the fluid times the fluid displaced by the object is equals to to what? Area times HF, right? That's the volume, this volume, okay, equals to density of the object times what is the volume of the object, gonna be area HO, correct? Perfect. And then area is cancelled. And what do we have? Well, we have, for example, that that density. We can solve for, let's say, for any quantity. Again, what do we have? We have density of the fluid displaced, height of the fluid is equals to density of the object, correct, times the height of the object. We can keep it like that, or we can work what we can divide them, correct? For example, imagine that we're looking for the depth. Okay, imagine we're looking for this. How much is the block right inside of the water? Is equals to what? Is equals to density of the block, correct, of the object in this case, divided by density of the fluid times the this height of the object, right? For example, see, here we have again this equation. This is for point object. Again, when we're dealing with floating object, means what? That the buoyant force is equals to the weight of the object. That's the reason why ship, right, float, correct? Because a ship displaces a lot of water. The most water is displaced, right, the most force is acting outward to keep this the ship, right, floating, right? Using this condition, the Archimedes principle, the buoyant force is equals to the weight of the object when the object floats. Okay, perfect. So we can use this quantity or this equation, or we can use this equation, correct? Like in this case, what do we have? It's gonna be density, where am I? Right here, I'm right here, right? Of the object and h of the object, or also we can go to the floating object, buoyant force is equals to the weight of the object. Right? Perfect. And with this, we finished this video. This is part 1. The next one is gonna be part 2 for this chapter, fluid mechanics. Okay, thank you, see you in the next video.